So the second talk in this session is going to be presented by Mary from the Federal University of Technology Akure in Ondo State, Nigeria. Actually quite excited for this one. This is a talk looking at optimal control in a COVID-19 setting. So Mary, if you are available and online, please do take it away.
All right, thank you so much. So I want to appreciate the Institute for Disease Modeling and the Bill and Melinda Gates Foundation for the work they are doing, in combating infectious disease and ultimately helping to eradicate them. So my name is Ogumodimu Mary, and my presentation is on the sensitivity and stability analysis of COVID-19 and tuberculosis co-infection, presence of disease dynamics. I'm a PhD candidate at the Federal University of Technology, Akure. So this work is basically about looking at how to combat the co-infection of COVID-19 and tuberculosis. We've seen that active tuberculosis is a major risk factor to increase the spread of COVID-19 in any community. And even up until date, we've continued to see the co-infection of these two diseases, even with factors like treatment and vaccinations in place. But we realized that the co-infection continued to spread because some of the vaccinations we have are not 100% efficacious, in the sense that, for example, the BCG for tuberculosis does not give a lifetime immunity, in that people can get infected if they lose their immunity. Same for COVID-19. And in fact, in recent times, we've been seeing more cases of people who had previously been infected with either of this infection getting reinfected again. COVID-19, like we all know, is a disease that broke out in December 2019, and previous people have contracted it since then. There's a major risk factor for higher severity for COVID-19, and this is a pre-existing disease. That is, if the person is infected with a disease such as tuberculosis, cancer before, and then the person contracts COVID-19. So it can make the COVID-19 worse and even increase the mortality rate. Tuberculosis is an infectious disease caused by the Mycobacterium tuberculosis, and we have both the pulmonary and the extrapulmonary. But for the purpose of this presentation, we'll be dealing with the pulmonary infection of tuberculosis, that is the ones that affect the lungs and the organs that are associated with the lungs. So TB is the 10th leading cause of death worldwide since 2007, and is in fact the main cause of death from a single infectious agent, ranking above HIV/AIDS, according to research by Slater and others in 2021. Now, this figure shows the active COVID-19 cases globally, and as we can see how it started in late 2019 and then progressing thereon. We can see the peak around February 2022. And then it started gradually started declining. It has some peak and then decline. But we noticed that looking at recent times, majorly for the purpose of this research, we looked between 2022 and 2024. We saw that there was a peak between December 2022 and February 2023, and after which there was a uniform. It maintained a uniform state, and then there was a peak again in between towards the end of 2023 and then the first quarter of 2024, according to odometers. This is the growth factor of daily new cases of COVID-19 worldwide, specifically between January 2020 and 2024. We can see that even though there's been a reduced growth factor, but towards the end of 2023, we see a very major peak in this growth factor, having 6.53 in January 23, 2024. And this simply means that people are getting reinfected, or there's a reemergence of this COVID-19 between October 2023 and January 2024. The growth factor simply means at which quantity multiplies itself over time, and this by dividing the previous day's cases by the new cases on the following day. This figure shows the global number of people treated for tuberculosis disease between 2010 and 2022, according to the World Health Organization. We can see that between 2020 and 2021, there was a little drop compared to previous years in the people treated for tuberculosis. And this was associated with sudden emergence of COVID-19, leading to limited number of people who were diagnosed for TB but yet couldn't get their treatment, because now so many people had to focus on receiving treatment for COVID-19 in these 2 years. But then in 2022, after a little stability with COVID-19, we saw a peak again in the people treated for tuberculosis. Now, co-infection of COVID-19 and tuberculosis, according to a research by Tadolini in 2020, states that higher rates of co-infection between COVID-19 and other respiratory pathogens are experienced compared to co-infection with other diseases. So TB, which means that TB and COVID-19 can have higher rates of co-infection compared to COVID-19 and other diseases. Also, we note that TB and COVID-19 have the same route of infection, that is respiratory organs, the lungs, and so on. And thus, they potentiate their effect on each other, and therefore they can mutually accelerate their progression to a critical stage, that is for someone who is infected with both diseases. Also, according to Kuna and Agrawal in 2020, it says that both TB and COVID-19 disease spread in overcrowded areas. And so someone who has a previous infection with either of the two can easily contract the second one, because it simply means that the person is in the same environment that is that can predispose the person to either of the two diseases. And this co-infection with the two diseases have 23% mortality. Also, due to the unprecedented nature of COVID-19, some cases of tuberculosis in people which have not been diagnosed before got diagnosed because they were in the hospital or in the health facility to be diagnosed for COVID-19, only to find out that they had a subtle case of tuberculosis. Would see in the model development that tuberculosis can either be latent or active. So people who were previously infected with tuberculosis at the latent state, who have not been diagnosed, were in the health facility just to be diagnosed for tuberculosis. Now, the first ever global cohort of TB patients in 2020 by the Global Tuberculosis Network looked into 8 countries in 3 continents, and it was found out that out of the 49 patients they reviewed, 26 of them had TB before COVID-19, 14 had COVID-19 before TB, and 9 had both diseases diagnosed within the same week, while 4 were diagnosed on the same day. Similarly, a case study analysis of this co-infection by Stoshino and other researchers found out that among the 24 inpatients diagnosed with tuberculosis, 20 of them had co-infection with COVID-19. This is just to see that there's a large percentage of people that has this co-infection of tuberculosis and COVID-19. Now, the development of the model, the mathematical model we developed is a compartmental disease model, and it has 12 compartments. That is the susceptible compartment, the COVID-19 infected, then the latent TB. Like I said earlier, that actually 1/3 of the world's population is infected with latent tuberculosis. But at this latent state, you rarely show symptoms of the infection, so you rarely get diagnosed. So this IL covers for the latent TB infected population, then the active TB infected, then we have the co-infected with COVID-19 and latent TB. We have the co-infected with COVID-19 and active TB. Then the RC represents the COVID-19 recovered population because we incorporated the treatment parameter. And then the TB recovered population. We have the COVID-19 and TB co-recovered population, that is if they recovered from the two. Then COVID-19 vaccinated population due to the vaccination parameter, the TB vaccinated population, and then the co-vaccinated population. So these are the parameters that are involved in the formulation of the model. I may not be able to go through each of them, but we'll see them in the schematic flow diagram. This is the developed co-infection model for the two diseases, and then this is the schematic flow diagram for this co-infection. So this flow diagram simply shows the interrelationship between this individual subpopulation. For example, how the susceptible population relates with the vaccinated population for COVID-19. Parameter nu C here represents the vaccination rate, moving a particular person from the susceptible class to the COVID-19 vaccinated class, while parameter omega C here represents the loss of immunity for vaccination, because we found out that people who have been previously vaccinated could lose their immunity and become susceptible again, thereby being able to contract the infection again. So this omega C represents the immunity wane. Also, omega T represents the immunity wane for tuberculosis, because people who have previously been vaccinated for tuberculosis can again lose their immunity if they continue to be exposed to an endemic area, and then they become susceptible again. So we have the other parameters involved in the model. We have the mu being the natural death rate, while delta C is the death rate due to COVID-19 infection. This is delta C here. And delta T is the death rate due to infection with tuberculosis, this delta T. And then the other parameters are shown in the flow diagram. So what we did again is to develop individual models for COVID-19 and also for tuberculosis, so that we're able to compare the result of our analysis and simulations, that is comparing the results for people who are only infected with COVID, those who are only infected with tuberculosis, and then those that are co-infected. So this system of 4 ordinary differential equations represents the model for the infected, for the COVID-19 population alone. And this schematic flow diagram describes the COVID-19 model alone. This is the susceptible class for COVID-19, the infected class, the recovered class, and then the vaccinated class for COVID-19. And then we also developed a model for the tuberculosis disease. So this is the model representing the tuberculosis infection, and then this is the flow diagram for tuberculosis infection alone. So next thing we did is, for any mathematical model, there are analysis that needs to be done to guarantee that this model is in fact able to represent the real life situation being described. So we obtained the invariant region of the model, that is the bounded solution of the model, the bounded state in which the solution to the model exists. So we're able to perform this invariant analysis, and we're able to obtain the bounded solution region, which is this NT exists in N naught, lambda over mu. So we're able to show that the solution to this model exists in a bounded state in which both the lower bound and the upper bound are positive, because human population is non-zero, cannot be negative, is non-negative rather. Also, the second analysis that is very important is the positivity. We need to be able to show that all the classes or the subpopulations in the model representing the real life situation are in fact positive. So we're able to show for each of these compartments, the susceptible class, the infected class, and all the other class, that the solution to each of these compartments or each of these ordinary differential equation is in fact positive. Then another thing we did was to perform some parameter estimation, because we didn't just want to get our parameters from previous literature, since we wanted the solution to model what is presently existing. So we used Nigeria as a case study, and we were able to obtain some data from Worldometer and also from the Nigeria Center for Disease Control. So using this data obtained, we're able to estimate the value for the natural death rate of human, which was obtained as this. And because we simulated our model using the week, so we divided by 52. So this is the natural death rate of human, and then the disease-induced death rate is gotten by this. The recovery rate is gotten by this, which is 0.6, and also the rate at which people enter the susceptible class, that is the recruitment rate, is also gotten. So we're able to estimate most of our parameters, and then this is the table of values for the parameters. The next thing we did is to obtain the equilibrium point for each of the model. And basically what the equilibrium point is talking about is that if there exists a disease-free equilibrium, that is, there exists a solution to the model in which the population studied can remain absent from this disease. Basically, the disease-free equilibrium simply states that if this disease-free equilibrium solution exists, then it is possible to attain a state in which that population is absent, or the disease is absent from the population. So we obtain the disease-free equilibrium point, and then we show that we're able to establish that the disease-free equilibrium point is in fact stable. This is done by obtaining the effective reproduction number and showing that it is less than 1. If it is less than 1, then the DFE is stable. So based on the parameter we use, our effective reproduction number for COVID-19 was obtained as 0.4888, and for tuberculosis was obtained even smaller than COVID-19, which shows that if the parameters and the values that are used in this model are implemented in a real life situation, then we're able to obtain this effective reproduction number, saying that it is in fact possible to contain and ultimately to eradicate the disease from that population, because the effective reproduction number simply means the number of people that a single infected person will transmit the infection to throughout their lifetime. So if the number of people is less than 1, then it means that over a period of time, it is possible to eradicate this infection, keeping in mind that the parameters needs to be maintained at the values used. Otherwise, if the values should increase, for example, if the value for the immunity wane should increase, as we will see in the simulation results later, then of course it will increase the value of these reproduction numbers, and it might make it difficult or impossible to eradicate those infections. So we also performed the global stability analysis of the disease-free equilibrium. Then for the endemic equilibrium points, an endemic equilibrium point is the solution to the model's equation in which all the classes in the state variables in the model have positive results. And if they have positive results, it means that even the infected classes have positive results, and so the disease will remain in the studied population. So we obtain the solution to the model, that is this endemic equilibrium point. And then we also showed the stability of this endemic equilibrium point. So this endemic equilibrium point will be stable only when this reproduction number is greater than 1. And that is when the disease will persist in the studied population. Then we perform a sensitivity analysis. This analysis is very important in any co-infection or any disease modeling, because it shows the significance of each of the parameter on the model, both in the control and the spread of that disease being modeled. So, for example, if a sensitivity index is positive, it means that a particular percentage increase in the value of that sensitivity index will increase the reproduction number by that same percentage increase. For example, if we increase the value of, say, omega C by 10%, giving us 1.9, it means that we'll be increasing the value of the basic reproduction number or the effective reproduction number by 1.9%. And of course, we know that if the reproduction number increases, then it becomes difficult to control that disease, because you are increasing the number of persons that a single infected individual will spread the disease to. So meaning that parameters with positive sensitivity indexes will result in a continuous spread of the infection, while parameters with negative sensitivity indices will yield to a decrease in the spread of the disease, because they result in a decrease in the value of the effective reproduction number. So we can see parameters like VC, no C rather, which is the vaccination, gamma C, which is the treatment, having a negative value. And in fact, we can see that gamma C has the highest negative value, 0.97, which means that the treatment, it has the highest effect on reducing the spread of this disease, followed by the vaccination, and then the natural death rate. And then to increase the spread of the disease, we can see lambda having a value of 1. That is, it has a direct relationship with the basic reproduction number. So if you increase lambda, that is the recruitment rate of people into this particular population, if you increase it, for example, by 16%, you are also increasing the value of the reproductive number by 16%. Same follows for beta C, which is the contract rate, and also omega C, which is the loss immunity wane. That is, if the people continue to lose immunity at this particular rate, then any percentage increase in the rate at which they lose immunity will also increase the value of the reproduction number, and so increase at which the disease continues to spread in that endemic population. So we perform numerical simulations of the model just to be able to get results of our models and the different compartments in the model. We implemented the fourth order Runge-Kutta algorithm on MATLAB subroutine, and we have the following graphs. The time might not permit me to show all the graphs. So this graph is the susceptible population against time. We can see the decline in the susceptible population for the COVID profile and also for the TB profile. This is consequence on the fact that there is vaccination. And because of time, we will come back to the value of the vaccination. We'll see that because the vaccination is quite good enough, then the number of people in the susceptible class flow into the vaccination class. This is the vaccinated class. So we can see the increase in the vaccination class, both for COVID-19 and TB. This is the latent infected class for tuberculosis, we can see an initial increase and then a decrease in this value, even though the value did not converge at 0. In fact, as at the 88th week, we still have about 25 people being latently infected. And then we can see the infected population for COVID and then for TB. Because of the rates of the vaccination and the recovery rates, that is the treatment factor, we can see that period of time in which there was an increase in the infected population, then we observe a decline. And over a period of time, we saw that, in fact, the number of people infected with COVID-19 was able to approach and converge on 0, even though the number of people infected with tuberculosis did not have the same result. We can see that even after the 88th week, the people infected with tuberculosis were still at about 4. Then we have the recovery rate. We can see a continuous increase, a slight decline, and then we can see that the value of people recovered was maintained slightly at a good value, even though we would expect that recovered class should continue to increase. But because of the parameters of disease relapse, which is one of the major things that made us go into this research, because of the parameter of disease relapse, that is people who have previously recovered from the disease getting it again. So we saw that there was a quite decline in the recovery rates, even though this decline is not too much. And then for the TB population, then we varied some of our parameters, that is using different values for each parameter so that we can see how fast the disease will continue to spread or reduce in its spread. So we varied the contact rate, that is the contact rate between an infected person and a susceptible person. So increasing the value of the contact rate, we can see the effect that if the contact rate is in fact very small, we would see that the number of people that will be infected with the disease will be very low. So that just states that bringing the contact rate to a very low value will mean that a very small number of people will be infected by this disease, and just over a short period of time, in 5 weeks, people might no longer be infected with that disease based on this value used. We can also observe the same thing for the vaccinated population. That's for COVID-19. We also vary the parameter of disease relapse. That is, if we increase the rate at which people relapse or get reinfected by this disease after recovery, we see the effect on the infected population and also on the recovered population. We see that if the disease relapse rates increase, then there will be a higher number of people getting infected and a lower number of people recovering from this disease. We also vary the vaccination rate. This is the effect.
Sorry to jump in. Maybe we're just about out of time. Maybe if you could skip ahead to your conclusion slide. Yeah, thanks so much.
Okay, so in conclusion, and then for some recommendations, the result of the stability analysis shows a stable DFE, like I already said, and then the sensitivity analysis was able to tell us the rate of sensitiveness of each parameter. So we recommend awareness and sensitization as it should be, and especially in countries in which they might live in overcrowded areas. So sensitization should be performed or should be done continuously. And then very importantly is the awareness of efficacy of vaccination. And in fact, particularly for health agencies and institutions to look into if it's possible to get an 100% efficacious vaccine that will give a lifetime immunity for tuberculosis, so that people who have been vaccinated can no longer contract the infection, and also for the treatment, so that people who have been treated can no longer lose their immunity, such that they go back to being latently infected by the infection. That's for tuberculosis. Availability of point-of-care diagnosis, especially in developing countries and endemic areas, point-of-care diagnosis should be made available so that people can to reduce the recruitment rate and also the contact rate, so that people can easily get diagnosed and know if they have this infection or not. Thank you for listening.
Thank you so much. That was an absolute tour de force. Holy cow. I saw many things there. I like the Lyapunov functions and the stability analysis, a very deep look at how to use these types of models. I think in the interest of time, unfortunately, we're going to have to move on, but I would ask if anybody does have a question, please do drop it in the chat. And Mary, if you're able to just check there and see if there are any questions you might be able to address. So we'll move on with the program. Thank you so much, Mary. One more round of applause. Thank you.